All right. Welcome to the second episode of Author Meets Physics. This is your one-stop shop on YouTube for in-depth discussion of recent work in the philosophy of physics. So today we have Marian Gilton as our guest. Marian is assistant professor of history and philosophy of science at the University of Pittsburgh, and the author of another of my favorite recent papers in the philosophy of physics, Could Charge and Mass Be Universals? Marian, welcome.
Hey, Dave, it's great to be here. Thanks so much for having me on the podcast.
Yeah, my pleasure. Okay, fantastic. Um, so this essay, it's an extremely rich essay. It does a couple of things that I really enjoyed. It provides a kind of I think in some ways, especially with some in some places, very decisive refutation of an important paper in the literature, which is Tim Maudlin's paper, Suggestions from Physics for Deep Metaphysics. And then it also kind of within the framework that Maudlin sets for thinking about physics and metaphysics, you accomplish some further things in this paper and kind of provide us with a bunch of interesting musings about properties in physics. So there's a lot that I kind of want to see if we can get to. So I'm thinking a natural start would be just Tim Maudlin's original argument.
Yeah.
So if I understand the argument correctly, Tim is saying, well, certain properties in physics, the kind of central example being quark color, but an example he uses to illustrate this is just the direction of a vector. They can't be understood as universals the way that David Armstrong or David Lewis would say, because or they can't be understood as metaphysically pure, as Tim puts it, which is kind of like this maybe term of art that he uses to precify the notion maybe of intrinsicality or something. Did you want to kind of summarize the argument, or I'm happy to?
I'll just my reading is that the takeaway is you can't have any universals the way Lewis and Armstrong would think of them. And I read Maudlin as targeting universals even more broadly than just those two, sort of the whole tradition of universals back to Plato and Aristotle. Mm-hmm. And it comes down to the use of fiber bundles in physics. Well, because the theories in which we have these properties that should be playing the role of universals are formulated in fiber bundles, and because of how things work in fiber bundles, you can't have any universals. And as you were describing just directionality, this is the sort of basic picture of a fiber bundle to kind of turn to see why something weird is going on with fiber bundles. So the standard example is to look at, say, a sphere, which is of course curved, and imagine vectors at points on that sphere, and at different points, maybe up at the North Pole and then down at the equator, and try to answer the question, well, are these two arrows or these two vectors, tangent vectors, pointing in the same direction or not? And if you just sort of play around with a couple of arrows on the surface of the sphere, you'll quickly realize, okay, this actually turns out to be path dependent. It matters how I parallel transport, which path I actually take to move one vector to the other, to then determine, well, do they in fact coincide or not? But subtly, it's more than just path dependence.
Yeah, good. So right. So to Tim, it's kind of important that that what's going on here isn't just the two vectors and their directions kind of by themselves. It's like you have to have a third object here, the connection. Yeah, in order to determine how that sorry, I didn't mean to be interrupting. I was just kind of like, I was kind of like visually illustrating the path dependence of parallel
Yeah,
transit.
yeah.
Um,
Good.
yeah, good. Okay, and so as you would agree with Tim, at least the values of some quantities like quark color, which we would have thought maybe naively um, to be kind of like just intrinsic properties, have this path dependence feature too. And yeah.
Yeah, that's right. I think that's where Tim and I definitely agree, that at this particular place of looking at properties in physics, specifically color state, so red, blue, and green of quarks, and then the appropriate sort of combinations of color and anti-color for gluons, and of course anti-color for anti-quarks, at that sort of maximally specific level of an individual color state, the way that kind of property is represented in the fiber bundle formalism is with a vector, an element of a particular vector bundle. And without a connection, you can't answer questions of, is this vector over here in this fiber the same as the vector over here in this fiber?
Right. And, uh, certainly the way that Lewis thought about things was you can just straight up answer the question of whether two objects have the same fundamental property at different locations. Uh, you know, this is clearly something that at a minimum kind of like wasn't on his radar, right?
Yeah.
Um, yeah, good. And Maudlin takes this to be a kind of refutation of that picture of universals. Importantly, he thinks, for reasons that, as we'll see, you kind of disagree with, he thinks like no properties can be universals of this sort.
Yeah, he says a wholesale revision of the
Yeah,
whole picture of universals is called for.
yeah, good. Where as we'll see, you kind of reach a more moderate conclusion. Yeah, good. So at this stage, there were a couple of things. So this deep metaphysics paper of Maudlin's is one that's kind of existed for many years. So long ago that a kind of like uh, I don't know, like at least middle-aged dude like myself was in grad school when the paper was originally being kind of presented and floated around. And where I went to grad school, Maudlin gave a talk on this, and I remember the metaphysicians being underwhelmed and saying, "Well, why can't you just say that in this case the fundamental thing is a three-place relation between one quark, another quark, and the path that gets you from one to the other, or one location's probably better to say SU3 field value and another location's value, and the path that you take to transport between them." So I'm wondering what you think of this kind of like very early way of getting off the boat from what Maudlin is saying.
Yeah. So I think there's something that's on the right track with that kind of response. Like, so it's relational. Okay, great. Especially from the purview of sort of metaphysics very broadly, we have accounts of relations, lots of them, right? Like, that's not a major problem. But for the Humean, perhaps it is still this big problem, right? Because the expectation was physics is going to give me the correct list of perfectly natural properties. I get to sort of fill out the tiles of my mosaic using these properties. And from there, I then get to account for objective similarity and the laws of physics, and do all the rest of the grand metaphysical project that I want to do. And the trouble seems to be that you would have expected the tiles of the mosaic here to be capturing one little fact of the matter after another in this maximally specific way. And so you'd expect the maximally specific sense of color charge, these specific color states, to play that role. And taking something that's supposed to be, that's that specific, and turning it into a relation, I think does throw a pretty big wrinkle in that larger project, in that Humean project.
Yeah, good. Yeah. Yeah. So I mean, maybe one way to kind of see this is of a piece with some kind of like, there's a lot of recent work that's um taken something like a broadly Lewisian metaphysical picture and been like, well, what happens if we kind of don't try to be so Humean about it? I mean, one example that's dear to my heart is uh Shamik Dasgupta's work on the metaphysics of quantities, where like the facts that undergird something having a mass or a charge are things like comparative relations between what we would ordinarily think of as the intrinsic mass of one thing and the intrinsic mass of another thing, when really like what's basic actually are things like this thing is more massive than that thing, this thing is like twice as massive as that thing or something. And yeah, so maybe kind of maybe this is more localized to Lewis's specific picture than Maudlin saw it as being.
Yeah, that could be. I mean, I think the fact that the target here is the stuff that's most fundamental really does matter, right? So like if you take a sort of broadly Aristotelian approach, like there's nothing problematic with having relations, right? It's like one of the 10 categories, it's great relations, no surprise whatsoever. But the details of how this is supposed to work out at the most fundamental, or sort of the most fundamental level in the sense of smallest, for Aristotle is sort of notoriously really difficult, right? And that's sort of the alternative to humanism that I'm sort of most familiar with. But there, you end up with a pretty major revision to the first category of substance, like what even counts to be a thing, that muddies things a good bit. So, I mean, maybe just sort of pull things back to this issue of specifically color charge. I think when you look at QCD and how color charge actually works there, it'd be a mistake for any kind of approach of naturalized metaphysics to not take seriously the sense in which this thing is relational.
Yeah, cool. I mean, yeah, and nice preview too. What another thing we'll be touching on is some of the interesting stuff where you bring in a kind of more Aristotelian picture to these questions. So that'll come up again later. Okay, so moving on to what you say rather than just what Maudlin says. And yeah, this is actually a good place to kind of bring in that question about Aristotelian universals. So if I understand you right, your picture is, well, an Armstrong or Lewis style universal has to be something that is kind of like completely determinate in the sense of, so by analogy with like the determinate determinable distinction, there are a lot of ways of being read, right? So therefore, a truly basic property couldn't be being red. It would have to be being like this specific shade of red, this kind of measure zero line on the color chart or something.
Yeah, for macroscopic color.
Yeah, exactly. Right. If we were to suppose that macroscopic color was a candidate for being a fundamental property, which of course, it's not a good one. But you would need the fundamental properties to be completely determinate. Whereas you understand the kind of Aristotelian style view as one on which basic properties don't need to be completely determinate. Am I
Yeah.
kind of getting the view? Yeah, good.
Yeah, for sure. Yeah. So I mean, it's right. Yeah, it's centering on this issue of different accounts of universals. And I do take Maudlin to be saying the whole tradition at this very broad level has to be jettisoned. One thing he is very clear of is that he's using the term universal as representative. He's supposed to be read as also targeting trope theory, natural sets, these sorts of things. Yeah, and so with that kind of expectation in mind, that the target of investigation here is a long-standing tradition of a notion of a universal, I think it becomes clear that for the details of how all this shakes out with fiber bundles, sort of what the takeaway is for you as a metaphysician or a philosopher of physics, it matters what version of universals you cared about, right? So I think, yeah, as you were saying with the kind of Louis Armstrong picture, like the whole goal is to say physics is this mature science. It's giving us the best candidates for fundamental predicates yet, right? We can sort of trust what physics is telling us are the sort of good candidate predicates for carving nature at the joints, for getting down to what's really going on there at fundamental, basic, elementary sort of levels. And because of that, I think the expectation there is you do need maximal specificity, right? You want one little matter of fact after another, and a sort of completely filled out matter of fact. Here is a quark with all of its particular properties, and there's another one, and so on and so forth. But that we should recognize that that's not the only way to think about fundamentality. That's not the only way to think about universals. Aristotle, for his part, and I think this probably should fit with Plato too, and kind of this older tradition of universals. They're generally more abstract. They're generally not the most determinate thing. Right? They're universals because they actually collect some things together.
Right.
And the way they do that is by abstracting from various particularities or accidental features. And so on that view, right, maximally specific color states, you might still have thought, okay, well, maybe I can get a universal going here, where I could kind of collect all and only those quarks that are in the red state. And then you're kind of surprised, oh, I can't do that. But you would still expect that there'd be an abstract level above that would still count as a universal. And I argue that you've got two of those when it comes to color charge.
Good. Yeah. Yeah. So you think that first of all, like having a color charge at all is a universal, and second of all, or it can be understood that way, and second of all, which fundamental representation of the color charge symmetry group the state belongs to is another good candidate for a universal, which tells us like whether it's a quark or an anti-quark in the case of quarks, right?
Yeah. Yeah.
Good. So the question I had here is whether, and it sounds like the answer is maybe no, whether you think there's any sense in which the specific values of the quark field, like this quark's color, whether those things can in any sense be understood as like Aristotelian universals, or whether we're going to need, are we going to need kind of like a metaphysics with maybe two types of categories, the things that are Aristotelian universals, like whether it's a quark or an anti-quark, and then something else that determines whether it is like quote unquote red or blue, to simplify a bit.
Yeah. So I think the answer to that, like, is it possible to account for the level 3, what I call level 3 color states as universal, or sort of maybe as something else within Aristotle's categories, right? Like he's got quantity and place and all these kinds of things. I think that's actually going to turn on what sort of account we give of quarks themselves. And at the moment, I kind of think there's like this epistemological tie, like there's a real kind of dilemma here as to whether we should think of quarks as real independent entities unto themselves, right? So this would be the classic Aristotelian notion of a substance. Or if, on the other hand, we should think of them as some kind of like partial being, and you don't really ascend to the level of a real substance till you get to a hadron. So, and so let me just say a little bit why I think why it's not clear.
Yeah, that's interesting.
Yeah. So first of all, we know that quarks are of course confined, right? We don't actually get to sort of pick one apart and ever detect just one. But beyond just confinement, there's a couple more wrinkles here. So when you actually write out the Hamiltonian for QCD, you can show that individual quark states aren't eigenstates of the Hamiltonian. And so you might have thought that usually in physics, the things that we would want to interpret as real independent entities should have determinate energy. And if you're a fan of the eigenstate eigenvalue link, you'd sort of add that in here to say, oh, look, well, now quarks don't have determinate energy unto themselves. That's weird, right? Maybe they're not substances. In addition, right, it's down here at this level 3 maximally specific state where we've got gauge dependence. So a gauge transformation is going to take, say, your red quark into a blue one, and would also transform all of the other quarks such that their relative colors stay the same. They're either all the same or different in the same ways. But if you kind of follow the standard line that gauge dependence of this form means it's not physically real, then this is another kind of piece of evidence that okay, quarks aren't substances. They've got these gauge dependent quantities that kind of rules them out. And I think all that's kind of suggestive, but then kind of counterbalanced by a couple more observations. So, right, which are basically the all of the empirical evidence we have in support of the existence of quarks and in support of color as a real property that we need to do good physics. So the first is it's these deep inelastic scattering experiments that showed that the electric charge of protons isn't uniformly distributed, right? So protons got charge +1, but it's not evenly spread out. It's actually in these little, pushed into little corners of the proton. And so you say, oh, okay, I can explain that if there are quarks, right? It's the charges of the quarks themselves that account for that distribution of electric charge of protons. So that makes it seem like quarks are substances because they're grounding the electric charge properties of the proton in the way that we usually think of electric charges as summing up. And I think even more importantly is the evidence for color itself and the role that it plays in getting predictions to actually fit with experiment. So if there are a few of these cases you can find in most particle physics books or books on QCD, where you get the statistics wrong by like the precise factor of 3 if you don't account for the color states of incoming and outgoing quarks, right? You've got to sum an average over them. And so in that sense of kind of accounting for the possible differences that matter for the statistics of actually getting predictions in scattering experiments right, that seems to suggest that quarks are substances, right? Their color properties really matter in terms of getting these things to go through. So all that to say, at the end of the day, if quarks are substances, then I think there might be something like really metaphysically revisionary going on in terms of accounting for their properties solely relationally without a sort of intrinsic ground underneath those relations. And if they're not substances, then I think there's probably something else metaphysically revisionary that has to be done, which is how you account for hadrons, things like protons, neutrons, and so forth, as having within themselves somehow these partial beings, right? Like quarks are somehow not fully real, but constituents of the things that are real. And I don't know of a place in metaphysics where that's sort of already been worked out and could just kind of account for
that's
that.
interesting. Right. That's I'm not sure I can think of something. I mean, I guess like I guess you could see the way that some trope theorists kind of think of tropes or something as like this. Like it's like a trope isn't, like a thing is built up out of multiple of them, and one by itself kind of isn't necessarily a thing or something. But yeah, it's not a perfect analogy by any means. I mean, so one of the things I was wondering as you were describing this kind of bifurcation into two possible pictures, I wonder whether the quarks are substances view gets more or less plausible if we think of quarks as being like, on a kind of field interpretation as opposed to a particle interpretation of them, like the quark field rather than the quark quanta or something.
Are fields allowed to have indeterminate energy?
Yeah, right. I mean, maybe, so well, so famously, like the gravitational field kind of does, right? In general relativity. For very different reasons, right? But it's like it's very hard to say what is the energy of the gravitational field in general relativity, and yet I mean, like, people don't tend to see that as a reason to not say that like the metric, aka gravitation, aka space-time, is like a legitimate physical field.
This could be interesting to see how much of those sorts of issues carry over here or not, right? Because you get all kinds of worries about the status of space-time and space-time substantivalism. So
yeah, for sure. And I mean, like another thing probably to just point out here by way of kind of like not leaving relevant alternatives unturned or something is that there are a bunch of kind of like purely kind of operator based ontologies for quantum field theory that people have talked about, like Wallace and Timpson's space-time state realism, where like you kind of forget entirely about things like the quarks and the electrons and stuff like that, and instead you say, well, like really there are the density operators, and those are the things that are kind of taking on values in regions or something. So much farther from the way physicists think about it.
Sounds a lot like math and not so much like the physical world, but
I think, I mean, like 100%, the thing that's always puzzled me about these views is like, well, how do you say that material things are made up out of this stuff, right? Whereas if you did have the happy situation of being able to say, well, there are real quark particles or like real quark fields that kind of come into states that turn into like hadron particles if you zoom out far enough, then you've got like, here's how we're made up out of this stuff, right?
Yeah. That sounds like physics to me.
But. Yeah, good. Yeah. No, I mean, like there's a lot to say there, but I share that concern about those kind of pictures. Okay. So where we're at so far, Maudlin has said, look, there's no fundamental properties that are going to be usefully understood as universals. Your suggestion is, well, if we understand them as Aristotelian universals, where they don't have to kind of be like, they can still be legitimate universals, even if they're not fully basic in the sense of completely narrowing down which determinative and determinable they are. Then you can say, well, like some things that don't change under parallel transport are whether this quark has color charge at all, whether it has, like a quark type color charge or an anti-quark type color charge.
Yeah.
I
should jump in and just clarify that I think it's more than that. So that's all I think accurate as to how I think about color charge. But it's important that there are these issues about, does this generalize to electric charge and mass?
Yeah.
And I think on the electric charge case, what you find once you've sort of seen color charge in this threefold manner, what you find is that when you try to apply that over with electric charge, that even though in principle you can do all the fun stuff mathematically with the group representation theory, really when you go to actually interpret what's going on with electric charge, it's degenerate. It collapses into just one level. And that one notion that you're left over with electric charge, it's just net amount of electric charge, passes the metaphysical purity test.
Yeah.
You can retain the Louis Armstrong view of universals as maximally specific. And the most specific notion of electric charge you'll ever get is net amount. And that turns out to be captured by the same place where you capture the difference between quark and anti-quark types of color. It's the different, right, the unitary, the inequivalent representations of U1 that are still irreducible, that capture different amounts of electric charge.
Yeah, good. Yeah, exactly. Right. This was, I mean, this was the part that I thought, given how one of the things that's I've always thought was a lot about the Maudlin paper is how kind of ambitious it is, generalizing from this example to saying, well, universals are done. I mean, I suppose, okay, well, I'll say that in a second, but like, but yeah, like this is a point of yours that's just kind of like impossible to disagree with, I think, which is, yeah, it's like, so in color charge, you have this direction ambiguity because the thing that doesn't change across parallel transport is how much color charge does something have. But there's a further question of what direction, quote unquote, in SU3 does that charge point, right? But if you look at a quark's electric charge, or if you look at an electron's electric charge or something, the amount is all there is to it. And it's not a quantity just because U1, the symmetry associated with electromagnetism, is just a simpler group than SU3. You don't have the question of which direction does the charge point. Good.
Should maybe be just a little careful and say simplistic, just because simple group is a
true. Yeah, right. I guess that's true. Like simple group is. Yeah, that's true. That's true. Good point.
But that's totally nitpicky. Yeah.
No, this is one of the things that one of the things that's always so frustrating about like talking about using mathematical terms and trying to use ordinary terms like they have, because so many mathematical terms overlap with ordinary terms. I've
Yeah.
been, this pushes my buttons because I've been working on something where I've been trying to, on the one hand, talk about representations of groups, and on the other hand, talk about scientific representation
Yeah.
in the same chapter. It's like, I mean, this kind of representation now.
Yeah.
Yeah.
Representation sub philosophy, representation
Yeah.
sub math.
I know. It's very
Yeah.
hard. Um, good. Okay. Um, um, like one of the things that's always puzzled me about the Maudlin paper is this move of saying, I mean, it's kind of like generalizing from one example to everything, right? Saying like,
Mhm.
well, we can't, there's a certain thing we can't do when it comes to quark color. Um, and therefore, uh, Louis Armstrong universals are out, as opposed to
Mhm.
saying, I guess you could, like, one thing you could say, of course, is, well, if you want to take the position that everything supervenes on Lewis and Armstrong style universals, everything is kind of like based on the values of Lewis Armstrong universals, everything boils down to those things. Well, like maybe that is sunk by this argument,
Mhm.
right? But like that doesn't seem to be how Maudlin is seeing the conclusion of the argument. So I guess like, yeah, I wonder if you could kind of like say anything to like alleviate my puzzlement about why he makes that move.
Yeah, yeah. So there may be a couple of things to say. Um, yeah. So I think one thing that's going on, hmm, I, yeah. So I do think that Maudlin is just being too quick, right? He's got one example, and the expectation of generalization seems to just turn on this claim that the way we represent properties in fiber bundles is with vectors, right? Um, and that just doesn't work for all properties, even though it works for some and in different ways. But maybe part of what's going on is this expectation in the background that all charges are alike, right? So working in the standard model, we've got QED, QCD, we've got weak dynamics. Each one of these has an associated charge. There's weak charge, there's color charge, there's electric charge. And maybe setting aside weak charge for the moment, we always, physicists, philosophers, everybody, we always introduce color charge as like electric charge, right? We know what electric charge is, that's familiar. Now we're going to move to this more interesting case of QCD where we've explicitly, actually, physicists explicitly built the theory as a generalization of QED. And we've got this new property, color charge, that plays this role in QCD that electric charge played over here in QED. And so with that kind of analogy in the background, that by definition, maybe even color charge is the analog of electric charge, you kind of expect that what you've said about color charge will, I mean, just sort of push it forward along the analogy and get the same result for electric charge. But of course, just because it turns out, just because these two properties, electric charge and color charge, play the same theoretical role in their two theories, right? The theories are different in large part because QCD is non-abelian, and that drives this big difference in terms of the group representation theory that makes color charge have this threefold conceptual structure that just collapses for electric charge.
Another thing I
Yeah.
thought of, just with the first part of what you were saying is like maybe his idea is that like so there's this kind of move. um I mean, I suppose he doesn't like this move when David Albert does it in quantum mechanics, but there is this sort of move that says when you want to interpret a theory, look at kind of like it should wear its interpretation on its sleeve, in the sense that the things that look basic when you write down the theory should be the things that are the basic properties the theory is talking about. And then you might say like, well, the things that look basic when you're talking about a theory in a fiber bundle are the vectors or something.
Mm-hmm.
And so like, so maybe the kind of like natural interpretation of a fiber bundle theory for him is one on which things like, you know, like mass and electric charge are kind of should be thought of as reducible to the things that look more basic in the fiber bundle representation of the theory or something.
Mm-hmm. Mm-hmm. Yeah, that's possible. I don't know, but even there, it seems to me, right, just that kind of approach you've just sketched to say, well, let's just look at fiber bundles. It kind of looks like what should be most basic there are the points in the fibers, and matter fields are sections of these bundles, and so that's what they're giving us, points in the fiber. But part of the point here, right, is these are gauge theories where the connection on the underlying principal bundle has physical significance. Um, and that's a field on the whole bundle, right? Then you can represent on base space, the base space on space-time relative to a section, right? If you pull it back. And the connection isn't giving you individual fibers, right? Like I think maybe could understand it that way if you build out the whole bundle of connections and then the specific one you're using is like a section of that bundle. But the point is just that if we boil things down to like just one of, not even the bare bones of, but just one of the bones of the formalism, you're probably missing out on a lot of other resources for your interpretation, right? So this is just one little example that beyond the fibers of one of the bundles that you use, namely the associated bundles for getting the sections that are the matter fields, whose sections are the matter fields, you've got this other piece of math in the formalism that plays this really important role, namely the connection. And even at that point, right, we've only kind of identified a couple of mathematical objects here, kind of at the level of the skeleton of the theory, without fleshing out how you actually do any physics with any of this. And I just, I'm more and more suspicious of these as a way of doing metaphysics, or a way of doing interpretations of physics, of overemphasizing the foundations or the bare bones at the expense of how you actually do any science on top of those foundations.
Yeah, good. So there's kind of like, this is similar to the kind of premises that you brought in when you were raising concerns about these density matrix interpretations. Okay, like good. This is great. I feel like this is going to kind of give the viewer, the listener, a sense of like where you're coming from as a philosopher. That's really cool. Awesome. Yeah, I mean, so this is also like kind of a nice segue to the next thing I wanted to ask you about, which it sounded like from our email exchange beforehand, this might be the place where there's the most kind of like difference of opinion between you and me. Is the question of like so some other structures that you can define are like potentially like fully invariant structures. So like Richard Healy, when I say fully invariant, I mean structures that don't change when you apply a gauge transformation to them. So in his book, Gauging What's Real, Richard Healy supports interpreting gauge theories in terms of holonomies, integrals of certain quantities around like closed loops in space-time. A bit debatable whether those are truly gauge invariant as opposed to being kind of like gauge covariant in the way that like a covariant vector is covariant in like relativity. So another possibility is Wilson loops, which are, like known to be fully gauge invariant. Like an interesting feature of these things is that they're properties of curves in space-time rather than being properties of points in space-time. Um, uh, so actually, that's a place where I feel like I can kind of see where you're going to raise concerns, along the lines you were just raising, like how real is this stuff? Like how much does this kind of feel, I shouldn't say feel, but just kind of like how much does this make sense of a picture of things as real physics, where objects are built up out of these things, right? But yeah, like what uh um do you see those kinds of interpretations of gauge theories as um a possible way to salvage Armstrong Lewis universals? If we say like maybe the universals are um properties of these curves in space-time rather than properties of points in space-time.
Yeah. Yeah. So, I mean, I should say I'm no expert on holonomies. And the little I've engaged with it, it's always been difficult for me to see how you define it without fiber bundles, like how this is a real alternative, because they're always at least initially defined on fiber bundle. But yeah, so maybe the Lewis Armstrong advocate can salvage the project and say, look, the fundamental tiles of the mosaic are these holonomies, these extended loops, these closed loops through space-time. And maybe you have to say, that's really not what I was expecting. I was expecting tiles to be smaller than this or less, of like, there are these extended loops that close around. That's maybe a sort of revision that you have to just accept. And I don't know, do you pass the metaphysical purity test? Can you say this loop over here is a duplicate of this loop over here? I don't know that simply gauge invariance gives you that.
Yeah, that's interesting. I mean, so yeah, I don't see why you wouldn't be able to, right? Because it's going to be like this loop over here gets assigned a number and this loop over here gets assigned a number. I mean, like there's the complication that the loops might be kind of different sizes and shapes and stuff like that. And so
Oh, okay. So
like maybe it would only be a candidate for comparison if the loops had the same size and shape by whatever definition of size and shape we're going to use in our interpretation of
okay,
space-time, right?
be up to diffeomorphism or something.
Yeah, right. So like, okay, yeah, so good. So like, so there's still the issue of parallel transport in relativity, because you're going to have to kind of like do a parallel transport to see, is this loop like, you know, uh kind of like of the same size and shape as this other loop, and that could change depending on how you parallel transport.
Yeah, so you might be right back at square one.
Yeah, interesting. Yeah, I mean, I think so. This gets to a place where it's a little odd the way that Lewis describes his program, if I can kind of like pontificate for a second about this, because he's like, well, everything is kind of made up of little, paintings on, painted dots on the mosaic, in the sense of like little perfectly natural properties at different locations. But you're saying like at different locations, so you do have to posit some fundamental relations, which are the fundamental relations that hold like spatially and temporally between the points, and those aren't going to be reducible to any mosaic stuff, right? So like I think this is why I mean, for one reason, for one thing, this is kind of like why Maudlin, I think, didn't just talk about parallel transport of vectors in space-time, but wanted to talk about parallel transport of color charge vectors. Because if he was just talking about vectors in space-time, then the Lewisian could come back and say, well, I always thought that there were fundamental relations, you know, between space-time regions or locations.
Yeah.
Can't do without those.
Yeah. So isn't this getting at kind of the rest of the Maudlin paper that I kind of just put as outside the scope of this paper, but it's, I think if I recall correctly, the larger kind of structure of the argument is to consider both the possibility and then rule it out of metaphysically pure internal relations, which is what color charge is about, but then also metaphysically pure external relations. And that kind of gets at all these issues about space-time and
good. Yeah, so like so then the thing that might be possible is for the holonomy person or the Wilson loop person to have a view where at least the internal properties are metaphysically pure, right? And maybe the only impurity comes in what happens when you like compare the spatiotemporal properties of one loop to the spatiotemporal properties of another loop.
Yeah, but so then on this modification of the Lewisian Wilson loop approach you're sketching here, the thought is you get to keep metaphysically pure internal relations and metaphysically pure intrinsic properties, but not the external ones. But you must also then give up color charge at level 3. That can't be one of the properties in your
Correct.
picture.
Yeah, that's right. It can't be.
Yeah, and so I guess that's where I would again kind of point to the role that these differences of color charge at level 3 play in accounting for the empirical evidence and the way theoretical predictions get made to go in alignment with the empirical evidence. You save the Pauli exclusion principle this way when you discover the delta plus plus and go, oh no, it's not obeying the Pauli exclusion principle. Well, now it is, because we've got color charge that gives us the differences we need. And again, what I mentioned earlier about getting the statistics right for a lot of these processes, yeah, if you don't have recourse to differences of color charge, I think you're going to be hard pressed to account for those pretty crucial areas of physics.
Yeah, good. I mean, yeah, so the view would have to be something like differences in color charge are real in the sense that like those can be reduced to, you know, they must be reducible to whatever the gauge invariant stuff is. But like color charge is not, so it's like you have differences in it, but you don't have it.
Yeah.
Or something we would describe as differences in color charge, but it's not truly differences in color charge. It's in some way reducible to the gauge invariant stuff. Yeah, I mean, and yeah, like I see why that would feel, you know, or like, you know, I see the argument one could make that that's unsatisfying, right? I mean, let me bring in an analogy that I like to use when talking about this kind of invariance issue. So relative phase in quantum mechanics, right? It's, you know, it's clearly legitimate to talk about the difference in phase between one part of a superposition and another part. And I, you know, there are dissenters from this, like David Albert read the most straightforward way is disagrees with this, but like for many of us, we don't think that the total phase of the state is a real thing. Only that phase differences between parts of the state in a certain sense are real. So I wonder if a picture like that would be, potentially okay. Like, yeah, like color isn't real, but color differences between subsystems are real.
Yeah, yeah, yeah. Where do you put that on a loop?
Yeah, right. Right. So like the story would clearly have to be like more complicated than that, because it's you'd have to say like, um what's the formula for getting to this from the loops, right?
Mhm.
Yeah, so like good. So maybe the kind of uh yeah, certainly this kind of view has the same kind of hurdle to cross that the Wallace kind of view of quantum field theory as a whole does. How
Mhm.
do you get from these unusual looking entities to normal looking entities? Right.
Yeah.
Yeah,
Yeah, but maybe those hurdles can be overcome. But yeah.
yeah. Yeah. No, but I like this is really helpful because uh it's it's doing a nice job of humanizing uh for me the view on which, like, well, maybe invariance isn't the holy grail of what's real and what isn't.
Mhm. Mhm. Mhm.
Which it kind of, that's always been my bias. So yeah, this is really really useful. um
Good.
Although maybe less useful because I'm still working on work that argues for this view. um okay, great. So we should talk a bit about the Higgs too. This is one of the coolest parts of the paper because it's been so hard to get work in philosophy that does a really clear job of explaining the Higgs mechanism. And I thought the paper did an excellent job of, just kind of like, I mean, of course not. This is one paper. One of the things that's awesome about the paper was how much was accomplished in a single paper. um, but as far as giving a kind of introduction to this idea that somebody could pick up and read a couple pages and feel like they've achieved some understanding of the Higgs mechanism, I thought this was a really great
Yeah.
discussion.
Good.
um,
Higgs 101 for philosophers.
yeah, exactly. Yeah, I mean, I think it's really, I haven't seen a uh better kind of treatment of this for philosophers, and anybody, I mean, you know like anybody who hasn't read the paper should read it, partly so that they can understand the discussion we're having better. But so there was a question I had here. So this is kind of you extending Maudlin's conclusion to a place where he didn't take it originally, because you point out, well, his argument for metaphysical impurity doesn't work for mass because mass is just a parameter in the fiber bundle theory. But here's another thing about mass that we know, well, we now know, like, thanks to the LHC, from particle physics, which is that the masses of all the ordinary particles that we measure come from their coupling with the Higgs field, um, via, like, symmetry breaking.
Mhm.
So that means, just like Maudlin has said, color charge can't be a pure internal property because it requires the connection in order uh, to make sense of even having values of that property. You say, well, in order to make sense of having values of mass, you need the Higgs, and
Yeah,
so
yeah.
mass kind of can't be. Yeah, go ahead.
Yeah, maybe just one more subtlety here. So I think you can make sense of the having of values for color charge at level 3 without the connection,
Sure.
but it's sort of useless for much of the metaphysics that you'd want to do, Humean or otherwise, I think, right? Because um, the sense in which you can have properties is all just relative to a given fiber. So you can say at point P, within this fiber, I have some value, and maybe pick your favorite basis of that copy of C3, and call the first vector in that basis the red state. Great, defined for that point. Now do it again over here at Q. You've got another fiber. You can again sort of pick your favorite basis and just say which vector corresponds to the different color states. But the thing is, without the connection, you can't make the identification across those fibers. So just a
Yeah, good.
little wrinkle.
Right, good. So like, you know, you can make sense of it in a sense, but only as a very perspectival thing, you know, kind of
Yeah,
like
yeah.
like what simultaneity is or something, you know. It's like, um you know, we can talk about it, but only as a kind of very particular feature that is had over here, not as a feature that this point could share with another point.
Yeah,
Yeah,
yeah.
which is
Which
really
of
cool.
course is hugely crucial for the Humean project if
Yeah,
you can't make sense of duplication and all this.
good, good. Yeah. So
We were talking about mass.
well, yeah, good. So that's interesting. This is something I hadn't thought of, but like, but that's not quite the same for mass, because once you have um uh the Higgs type symmetry breaking, then um you know, given that that field exists and has kind of like rolled down the slope of symmetry breaking in a particular direction, at that
Yeah.
point you can say, um you can make comparisons of
Mhm.
mass between one particle and another. So it's kind of like a bit different argument in a way, right? It's like the mass properties can't exist without this other entity. Um,
Yeah.
but that other entity, it's not like you have to like parallel transport via the Higgs field from one location to another to compare the masses of two
Yeah.
electrons or something like that.
Yeah. Yeah. We shouldn't think of like the Higgs as like the connection or something like
Yeah.
this. Yeah.
Yeah.
It's
Good.
different.
Good. Okay. So a question I had about this, and like this is partly just kind of like, you know, I coming from ignorance from me perhaps, but like, um, so the Higgs itself has mass. And so I was wondering if like, uh, the the desperate defender of metaphysical purity could say, well, there's one mass property that is metaphysically pure, namely the mass of the Higgs, right? I guess there's kind of two things. There's like the mass of the Higgs field and the Higgs like boson particle, and they're not quite the same thing. But like, you know, anyway, one of those two, or maybe both, one could say like those are metaphysically pure mass properties, even though the mass of like the W or the electron isn't metaphysically pure.
Yeah. Yeah. So this is great. Yeah. So the Higgs is said to generate its own mass, right, through self-interaction. And maybe one thing that's worth sort of noting is that, right, we usually, the evidence so far is just in support of one Higgs, but there's, as far as I know, still pretty lively research programs looking at the possibility of multiple Higgses, which would give you then potentially very different masses for each of the different Higgs, and
And
they could even.
then would their masses then come from like not just self interaction but interaction with the other Higgses? Is that how that would go?
I think you. I'm not sure, but I would suspect that you could have it either way. That you could
Oh
build
yeah.
some models where, right. So what you do is you've got these Higgs doublets, right? So you've got, in the usual way, just one doublet with 4 degrees of freedom, 3 of which become, or give you the, yeah, get eaten by the Goldstone bosons to then give you the W plus minus and the Z. Okay, so that takes care of 3 of them. The fourth one left over is the Higgs that we know and love. If you build out a second Higgs doublet, a Higgs doublet model, so we call these 2 Higgs doublet models, then you've got 4 new Higgses, but they can be charged, electrically charged, just as the W plus minus is charged. And so my guess is that you could have the generation of masses of the second one either be sort of the second one interacting with itself or also interacting with the first one. But I could be wrong about that.
Yeah.
My
Okay.
guess is you
Well,
could go either way though.
that's cool. I didn't even I actually didn't know about these models, but that makes total sense.
Yeah,
Um,
yeah. I think some of them are used for exploring candidates for dark energy and dark matter
cool.
and these sorts of things. Yeah, fun stuff. But
Yeah.
I guess
So
part of the point was just that in those kinds of extended models, right, if you've got, in fact, like 5 different Higgses, they can all have different masses. Some could be, heavier, sort of beyond current experimental ranges. Or
Yeah, good. So then rolling back, so like on the question of whether the Higgs mass should be understood as metaphysically pure, what do you think?
yeah, good. So let's take Maudlin's metaphysical purity test. Posit a world with just one Higgs in it, or I guess 2 Higgs bosons in it, but just one Higgs field. And let it be sort of after, I guess if it's after the symmetry breaking, you're going to have the W plus minus and the Z as well. But if we sort of allow that to be part of what it means to posit Higgs, then it's okay for them to be there. Then can you settle the question, do the 2 Higgses have the same mass? The answer is yes. You don't need to parallel transport them or anything. Their masses are just the appropriate numerical value you get when doing all the usual Higgs physics. And I think on my reading of Maudlin and what metaphysical purity is doing and all this kind of stuff, I think it would make sense to say that the mass of the Higgs is then metaphysically pure, because it's just the self-interaction. You don't need a third thing to get that off the ground.
Yeah, cool. This is a really useful way to kind of like put it, because it actually, it gets to the next thing that I kind of wanted to ask a bit, which is like something is a little confusing to me about the definition of metaphysical purity. Is what's the kind of like relevant modality that comes into it, right? So it's like something is metaphysically pure if it is possible for, like a property is metaphysically pure if it's possible for somebody to have that property, without requiring the existence of something else, right?
So I think what Maudlin actually says is just that that's a necessary condition.
Yeah,
It
necessary
doesn't
condition.
actually
Good.
give
Yeah.
us any sufficient ones. So I think at this stage, there's sort of, it'd be great for Tim to go write up something that then spelt out more fully what metaphysical purity is supposed to be.
Yeah, good point. Fair enough. Okay, so like necessary for metaphysical purity is a particular kind of like a modal requirement. Like, it has to be able to have this property without requiring the existence of other stuff. So if the notion of, it has to be possible to have this property under yada yada conditions is metaphysically possible, then we get into all kinds of hairy stuff about like property identity and whether properties would be the same properties if there were different laws. Like so somebody like Alexander Bird, or originally Sidney Shoemaker, would say if you have different laws, then it's got to be a different property. Properties are kind of identified, at least in part, by their role in the laws. If the kind of possibility in question is physical possibility, then it's like, it seems like we have all kinds of cases of metaphysical impurity, like having electric charge is metaphysically impure by that definition, because you can't have electric charge unless you're surrounded by a cloud of photons, right? Just the laws tell you that. So it's a little, it seems to exist in this kind of like funny liminal space where it's like metaphysical purity on the one hand is bracketing these questions about what it's metaphysically possible. What I'll put it this way: how could a property be metaphysically be different in different metaphysically possible worlds? Maudlin doesn't seem to want to get into that, right? But on the other hand, and I mean, to be fair, like that's not something you get into either, right?
Yeah.
And on the other hand, like if we're just talking about physical possibility here, it's pretty trivial that there's a lot of metaphysical impurity in physics, because there are a lot of laws that require one thing to go along with other things of a certain sort, right? So I'm a little confused about like what's going on here when it comes to that kind of issue.
Yeah. Okay. So you're thinking of physical possibility as constraining what can happen in some possible world according to those laws being true. So you
Yeah,
fix your world, the laws are all true. You try to instantiate something and you have recourse to all of the laws that are going to tell you what's going to happen. So in particular, if you've got electrons, you've got clouds of photons as well.
yeah,
Um, yeah, good. So um, and you're right, I don't get into this at all, and for that rhetorically is just the key point to be made really is one of, if you play Maudlin's game, he's wrong about electric charge, and that's really important, right? And here's why. But all these issues about property identification and metaphysical possibility plus physical possibility are fascinating. So I think we probably would be hampering ourselves if we didn't allow for some amount of property identification across theories, if only to account for the actual historical development of theories.
yeah,
So I kind of think of some kind of like, I don't know, theory space in which there's a neighborhood around the current best theory and it's pretty straightforward how you can identify properties across theories in that neighborhood, but then there'll be some boundary, maybe a vague region where it's unclear if you can't, but then beyond that you really can't identify things. And I think that comes into play here because one of the simplifications in all of this, like Maudlin's work and mine, all we need is a formulation of classical field theories in terms of fiber bundles. No quantum considerations have come into any of this at all. And so in that way, all of this is neglecting, I mean, I guess in the Higgs discussion, you've got to have quantum effects, but just sort of back to the basic fiber bundle points, parallel transport and all that, the messy details of the quantum aspects of quantum field theory have been completely bracketed.
yeah.
But you can still make sense of what color charge should be in the classical field theory.
Right. Good. Good. So like, so yeah. So in a way, like one of the things that's kind of being assumed here by all parties to debate is that you have a notion of the same physical property that makes some sense across theories, because sometimes like we're talking about classical theories, but we're talking about a world that isn't classical that we live in. Yeah, good. I mean, I definitely like, I 100% agree that you would have to like there's a significant worry that if you take these kind of really hardline views about property identity, where you can only have mass in a realm where all the laws involving mass are the exact same laws, yeah, like it's gonna be a little odd when you're talking about inner theoretic relations in physics. So yeah, I think I'm with you 100% on that count. Cool. All right. Well, like a lot of fantastic stuff about this paper, Marian. I've enjoyed talking about it very much. I have a couple of kind of like closing questions, which are like my generic closing questions for people on the show, and like answer them at whatever length you want. But one of them is how you're thinking about the topic of this essay has maybe changed or evolved at all since the publication of this. I mean, this is a really recent one, so legitimate answer would be this is what I think. But I wonder if there have been any kind of changes.
Yeah. So maybe just it's more sort of subtle words are hard, subtle shifts, or increases or decreases of emphasis. So yeah, so one thing that I think is clearer to me, or more significant to me now than it was when publishing the paper, is I guess kind of circle back to some of the discussion at the beginning, is the difference that it makes to this question, what you take a universal to be, which maybe is a little obvious, right? Like just from the title, but that the Humean approach really is different from the broadly sort of, I don't know, just the older view that universals can be these abstract things rather than maximally specific ones. And I think the more that I've thought about what Maudlin says, the more it seems to me that even though he pitches it at this very general level about sort of all universals, I think he's more motivated than perhaps he lets on in this specific chapter. Maybe it's clear in the rest of the book. Motivated by some of the details of the full Humean picture, right? Because these issues about duplication really matter, and can you freely recombine things? And moreover, from that way of construing the debate, there's something to be said for what Maudlin still gets at the end of the day, even though the argument doesn't generalize.
Yeah.
Right. If the whole Humean project is we're going to think of all of everything as getting built up from this mosaic of perfectly natural properties at the most fundamental basic level, if you get just one of those that doesn't fit, right, that's a major problem for that project. But kind of by the same token, if you step back and look at the larger tradition of what universals are, Maudlin hasn't done very much to make an Aristotelian or a Platonist sort of worry that universals aren't viable, right? What he's done is sort of raised, there's some really puzzling things about color charge to go sort out. I think that's like incredibly valuable, and metaphysicians of science should kind of pay attention here. But it's a major sort of deflation of the takeaway that you can't have any universals, right? Like it on this broader view of universals, the fact that color charge at the higher levels evades the argument is really significant, right? These are sort of what you'd expect to be universals if you follow the Aristotelian program of like, well, we're just kind of abstracting away from details and collecting things at that level, right? Like they just really, really fit really, really well there. But also, if you care about fundamentality, right? If you think that determinables shouldn't be fundamental properties, but you're not sort of wedded to all of Humeanism, the fact that electric charge escapes is really significant, because that's like, I think one of the best sort of candidates we have for a fundamental property, or for being a universal in that kind of sense, right? What other property has been studied for so long under so many formulations of physics, and that sort of accounts for such a host of physical phenomena, in terms of like this intrinsic property of constituent parts, right? Like the motion of electrons through a wire, something like this.
It's true. The electron is like the most long-lived fundamental entity kind of in the history of science, right? It's like, so it's got
Yeah,
a
it could
long
be.
history.
Yeah, yeah. So.
Yeah. No, and I like the first point too. I think, like, to be fair to Tim, what his opponents are saying, is like is refuted by a much weaker claim than the one he makes, right? His opponents are saying reality reduces down to properties, all of which can be understood as these fully specific universals. And yeah, like it's the points that he makes, even though they don't establish, as he suggests, that there are no metaphysically pure relations, they establish something that's still pretty hard for his opponent to take into account.
Yeah.
Yeah, great. So
maybe just
oh,
one other thing that I'll just mention, since publishing this, is that just the color charge has become even more interesting to me. Right, so we talked a little bit about this dilemma of quarks and are they substances or not, and I think there's so much there, and getting a handle on confinement and how all of that works for this property is is a place where there's really good work to be done. And that's one of these other sort of just really peculiar things about this property, right? It's never measured. It's a conserved quantity that's been around for what, 6 or 7 decades, something like this. Never once within that time has there been an experiment who said, look, we've gone out and measured color charge and here's the value, or anything at all like that. What other sort of conserved quantity is like that? So it's just this fascinating sort of bit of physics where I think there's loads more work to be done.
Yeah. I mean, unfortunately, some of that work has had to be done by physicists to figure out exactly how confinement works, right? But
for sure.
Yeah, like, I think at the same time, like, I think a lot of what we do can be valuable even if you do it at kind of intermediate stages of physics when it's not fully worked out. So
yeah. I hope so.
Yeah, I hope so. Yeah, I mean, like yeah, I given how much nice recent work there is about like quantum gravity, one hopes that that's true.
Yeah.
Cool. Okay, so then the other generic question to really end with is, did you have a new project or something that you're working on that you wanted to folks to have on their radar?
Yeah. So a few things kind of in the works here. So one is a kind of additional piece on color charge and what's going on with this that connects to what we were talking about earlier with inner theoretic relations and identifying properties across theories. So this is a project about viewing quantum color charge from the classical vantage point. So sort of arguing for methodologically the value of interpreting in a pretty serious, robust way classical field theories as part of the larger project of wanting to interpret quantum field theories, and really sort of fleshed out quantum field theories, like specific ones used in the standard model, not just quantum field theory kind of in general. And the thought there is that, or the initial observation there is that, well, the conserved current, according to Nurture's theorem for QCD, is Lie algebra valued. It's what you get with non-abelian gauge theories. I mean, it's Lie algebra valued for QED as well. It's just that the Lie algebra there is the real line, so you sort of don't look at that real number and go, oh, it's the Lie algebra. But you do for non-abelian theories, and so that's kind of curious, right? The Lie algebra for S2 theory is 8-dimensional. We always speak of color charge as this 3-dimensional thing. What kind of is going on there? So the project is to look at where that Lie algebra valued quantity for charge comes up in classical chromodynamics, right? Fictitious theory, but the way you would formulate it sort of fully before quantization, and then let's carry over to the quantum case. And the argument is that in the quantum case, right, the best candidate for an accurate theory, like current best physics, in the quantum case, this particular detail about color charge is obscured because of confinement, right? So again, You're never actually going out and measuring this quantity and saying, like, here's the particular Lie algebra valued quantity I got in this measurement. But you don't have confinement in the classical case. So if you go look over there, with some of those details sort of as important as they are, right, but not fully understood, and for the purposes of interpretation, kind of obscuring details about confinement set aside, you can go through this really interesting derivation of what's called the Wang force law, which is the generalization of the Lorentz force law. And when you go through all of those details, you see the thing that's playing the charge role, just as it does in the Lorentz force law. That thing is Lie algebra valued. So it kind of pulls this role of the Lie algebra for just defining charge properties in the sense of contributing to a charge current density, pulls that to the foreground. So
Very cool. I mean, this sounds like something I'll have to read in order to get it, but inducting on your previous work, I expect I will get it after I read it. So I'm very excited to read the paper, Marian.
hopefully.
That's great.
Yeah.
All right. Well, this has been delightful. You know, I don't know. I'm just loving doing this series. And yeah, I hope you've enjoyed this
So
conversation as
fun.
much as I have.
Yeah, for sure. Yeah, if you don't mind, I'd love to just mention one other project because
Oh
I'm
yeah.
really excited about it.
Yeah.
So I'm doing this collaborative project with Chris Mitch and David Freeborn. Both great folks I met at UCI while in graduate school and just kind of a couple of years apart from each other. And we're taking a look at some of the literature on Hogg's theorem in quantum field theory as a place of kind of getting a handle on some of these questions that came up earlier, like, well, what do we do with this, with the math? And maybe a little more broadly methodologically, like when you really put a finger on when the mathematical rigor or an axiomatic approach to a theory in physics is beneficial and actually sort of feeding back into the usual physics in a way that helps it move forward, and when does it become sort of disengaged from the physics in a less useful way. And so the project at the moment is the development of a framework for understanding all of the literature on Hogg's theorem, that sort of brings to the foreground some of the background commitments that people have about Hogg's theorem. So because this is this really concrete case that a lot of philosophers have thought about in terms of what Hogg's theorem says for quantum field theory. So looking forward to getting that project out.
Yeah, great topic. Another great topic. All right. I'm looking forward to reading it. Thank you so much, Marian. And I really appreciate this discussion and looking forward to having the episode out there.
Yeah, thanks so much, Dave. This is really fun. Glad you're doing this.
Awesome.